Now we got a bonus question. This says the graph of the continuous function g, the derivative of the function f, is shown below. The function g is piecewise linear for -5 less than or equal to x, which is less than 3, and g of x is equal to 2 times the quantity x minus 4 squared for 3, which is less than or equal to x, which is less than or equal to 6. Now this question's got 4 parts, so we're going to take it one at a time. We're going to start with A. A says if f of 1 is equal to 3, what is the value of f of -5? So the first and most important aspect of this question is to understand the relationship between g and f. This question says g is the derivative of the function f, meaning g is technically f prime. So down here, since we're given the graph of g, that means we're given the graph of the derivative of our function f. Not only that, but we are also given the y value of the antiderivative of g, f, at x is equal to 1, and it's equal to 3. And we're trying to find the antiderivative of g, our function f, at x is equal to -5. So we should set up an equation relating the derivative and the antiderivative in order to solve for f of -5. So what kind of equation relates the derivative and the antiderivative over a given interval? Well, that would be the fundamental theorem of calculus, which says the integral from a to b of f prime of x dx is equal to f of b minus f of a. Only in this case, our original function is f, just like it is here, but our derivative is not f prime. We're calling it g. So we're going to replace f prime of x with g of x. Now, how does this help us? Well, remember, the goal of this problem is to find f of -5. So one of these over here has to be f of -5. And we're also given that f of 1 is equal to 3, meaning the other one should be f of 1. So let's say our a value is going to be -5 and our b value is going to be 1, meaning we could rewrite this as the integral from -5 to 1 of g of x dx is equal to f of 1 minus f of -5. Now all we have to do is solve for f of -5. Well, we know f of 1 is 3, so we can substitute that in. That's pretty easy. But what about this? What do we do about this? Well, the integral from -5 to 1 of g of x dx is technically just the area between the function and the x-axis of the g function on that given interval. So all we have to do is find the area between the function and the x-axis from x is equal to -5 to x is equal to 1. Now looking at this figure over here, to calculate the area between the function and the x-axis, what we're going to have to do is use some geometric area formulas. Also remember that any area that is below the x-axis is going to be negative, any area that's above the x-axis is going to be positive. So from x is equal to -5 to x is equal to -2, we have a square with a base of 3 and a height of 3. Remember, it's below the x-axis, so that area is going to be negative. From x is equal to -2 to x is equal to -1, we have a triangle with a base of 1 and a height of 3. Remember, it's below the x-axis, so that area is going to be negative. From x is equal to -1 to x is equal to 0, we have no area because our function is on the x-axis. And then from x is equal to 0 to x is equal to 1, we again have a triangle with a base of 1 and a height of 2, but because it's above the x-axis this time, that area is going to be positive. So now all that's left to do is plug in what we said each of those measures were equal to and solve for f of -5. In order to do that, you just simplify over here, and you end up getting -9.5 or -9.5 is equal to 3 minus f of -5. So to solve for f of -5, we subtract 3 on both sides, divide both sides by -1, we get f of -5 is equal to 12.5 or 12.5. Part B wants you to evaluate the integral from 1 to 6 of g of x dx. So this question is pretty straightforward. It's just testing your knowledge on, do you know what a definite integral is? Yes, it's the exact area under the curve of this function on this given interval. So we just need to find the area under this function or between the function and the x-axis on the interval from x is equal to 1 to x is equal to 6. Now, because this is a piecewise function, there's a couple different shapes in here. From x is equal to 1 to x is equal to 3, we have a square. So we can find the area of that square and then add it to the area between the function and the x-axis on the interval from x is equal to 3 to x is equal to 6. So what's happening here is that from x is equal to 3 to x is equal to 6, we have this function, g of x is equal to 2 times the quantity x minus 4 squared. Now this is a quadratic function, meaning this is a curve here. So we can't use a geometric area formula to find the exact area between the function and the x-axis. We could use one to approximate it, but not find the exact area, which is what this wants us to do. So what we're going to have to do is we're going to have to break this up into two separate integrals. One would be the integral from 1 to 3 of g of x, and then we're going to add that to the integral from 3 to 6 of g of x. Now to evaluate the integral from 1 to 3 of g of x dx, we just have to find the exact area between the function and the x-axis from x equal to 1 to x equal to 3, which we said was this square. So we just do base times height. That's easy. But the integral from 3 to 6 of g of x dx is a little bit more complicated because we have a curve. So what we're going to have to do is we're actually going to have to evaluate this definite integral from x is equal to 3 to x equal to 6 6 using the fundamental theorem of calculus. So let's prepare this for integration. In order to prepare this for integration, we're going to take this constant 2, move it out front of the integral sign. Now what we can do is we can use the fundamental theorem of calculus to evaluate this definite integral. First step is to find the antiderivative of this given function in here. Well, because this is x minus 4, the quantity squared, what I want to do first is I want to take x minus 4, multiply it by the quantity x minus 4. I want to FOIL that out, and I end up getting a quadratic trinomial that looks like this. Now this is much easier to find the antiderivative of because I can just integrate each term separately. The integral here is going to be x cubed over 3 plus c. The integral here is going to be negative 8 times x squared over 2 plus c. And the integral here is going to be 16x plus c. Now, the c's combine to create one constant of integration, and because we're using the fundamental theorem of calculus, the c's technically cancel out, so we don't have to write it. We then evaluate this using the fundamental theorem of calculus. We take our upper limit of integration, 6, and plug it in for each of the x's. Then subtract when we take our lower limit of integration, 3, and plug it in for each of the x's. We simplify each of these parentheses, and then we multiply that 2 and the 3, we get 6. Add that to the 4, we get 10, meaning that the integral from 1 to 6 of g of x dx is equal to 10. Now part C says for the interval from negative 5 to 6, on what open intervals, if any, is the graph of f both increasing and concave up? Give a reason for your answer. Now if you recall, we are given the graph of g, which is the derivative of our function f. So we are given the graph of the first derivative. Now in order to find where the graph of your original function f is increasing or decreasing, you need to look at the y values of the graph of your derivative. If the y values of the graph of your derivative are above the x-axis, if it's positive, then you know the graph of your original function must be increasing. So the graph of your original function f would be increasing on the open interval from x is equal to 0 to x is equal to 6. Next, we have to determine where the graph of the original function f is concave up. Now remember, concavity is determined by the slope of the graph of your derivative, or the derivative of your derivative, or the second derivative. Wherever the second derivative is positive, that means your original function is concave up. Meaning wherever the slope of your derivative graph is positive, that means that your original function will be concave up. So by looking at the slope of the graph of g, or the slope of the graph of our derivative, we can determine what the concavity of the graph of our original function f is. Anywhere where the graph of our derivative has a positive slope is where the graph of our original function f will be concave up. So on the open interval from negative 2 to negative 1, our derivative graph has a positive slope, meaning our original function will be concave up. On the open interval from x is equal to 0 to x is equal to 1, our derivative graph has a positive slope, meaning our original function would be concave up. And then on the open interval from 4 to 6, our derivative graph has a positive slope, meaning our original function will be concave up on that interval. But this question wants us to find the open intervals on which the graph of f is both increasing and concave up. So we need to look at the graph of our derivative and determine where is it above the x-axis and where does it have a positive slope. So the graph of the derivative is both above the x-axis and has a positive slope on the open intervals from x is equal to 0 to x is equal to 1 and from x is equal to 4 to x is equal to 6. Therefore, our original function f would be both increasing and concave up on those two intervals. Now, one thing I want you to note is that when the AP test is talking about the derivative graph having a positive slope, the way they describe that is g is increasing. So just know that when g is increasing or f prime is increasing, they're talking about the derivative graph having a positive slope. Now part D says find the x-coordinate of each point of inflection of the graph of f. Give a reason for your answer. Now inflection points occur at x values where your original function changes concavity, when it changes from concave up to concave down or concave down to concave up. However, we are not given the graph of the original function. We're given the graph of the derivative. So again, it's important to understand the slope of the graph of our derivative, or the derivative of our derivative, or the second derivative is what determines concavity. So in the graph of our derivative, anywhere where we have a positive slope, that means your original function is going to be concave up. In the graph of our derivative, anywhere where we have a negative slope, that means your original function is going to be concave down. So we need to look for wherever the slope of our derivative graph changes from positive to negative or negative to positive. That's going to tell us where our original function is going from concave up to concave down or concave down to concave up. Now, like we said in the previous example, the AP test words this a little differently. Instead of saying the slope of f prime or g changes from positive to negative or negative to positive, they say that f prime or g changes from increasing to decreasing or decreasing to increasing. So again, we're just looking for the slope of the graph of our derivative to change from positive to negative or negative to positive. So from x is equal to -5 to x is equal to -2, the slope of the graph of our derivative is 0. Then at x is equal to -2, the slope of the graph of our derivative changes to a positive slope. Now, does that mean there will be an inflection point at x is equal to -2? No, because inflection points only occur when the slope of the graph of your derivative changes from positive to negative or negative to positive, not 0 to positive or 0 to negative. So there will not be an inflection point at x is equal to -2. For the exact same reason, there will not be an inflection point at x is equal to -1 because it's changing from positive to 0. Same thing with x is equal to 0. At x is equal to 0, your slope is changing from 0 to positive. At x is equal to 1, your slope is changing from positive to 0. So again, not an inflection point. At x is equal to 3, your slope is changing from 0 to negative. So again, not an inflection point. But at x is equal to 4, the slope of your derivative graph changes from negative to positive, meaning your original function changes from concave down to concave up at x is equal to 4, meaning there will be an inflection point in your original function at x is equal to 4.